Okay, so as we are in module number 1 here, we're going to click on module 1, and module 1 is going to pertain to chapter 1 in our machine and mechanisms book, and it's really going to be an introduction to mechanisms and kinematics. Okay. Additionally, our main focus there is actually two things. We're going to learn how to create kinematic diagrams, and then we're also going to learn how to calculate the mobility or the degrees of freedom for a mechanism once we have it together. So I'm going to click on my PowerPoint presentation here. This is a PDF. Okay. And I'm going to zoom out just a little bit so we can all see it. And then I'm just going to check with Logan. You're online. Are you seeing my screen right now? Chapter 1 PowerPoint. Yep, looks good. Okay, awesome. So as we look here, if you want to open up your book to chapter 1, we're going to kind of go through some of these sections. Now, something in kinematics, I just want you to be aware of as we go through the book. We're probably not going to hit each and every section in each and every chapter that we use, okay? So I use the PowerPoints as our guide through the chapter so that you know what you're responsible for, okay? So you're going to kind of see that play out here in chapter 1 as well. So the objectives here are really to, look at kinematics, kind of define what it is, and then also look at mechanisms as well. We're going to look at the different components that are going to comprise a mechanism. You're going to learn how to draw a kinematic diagram, and then also compute the degrees of freedom for a mechanism. Additionally, we're going to be looking at some standard 4-bar mechanisms, and then also identifying a slider crank mechanism as well, and calculating different things with that. So introduction here. So first and foremost, kinematics is going to be the study of the motion without regard to forces that cause it. Okay. So earlier somebody asked, is this like a continuation of statics class? It is not. Statics was all about forces and calculating reactions, and then strength of materials use statics to determine what are the materials or how much of that material do we need in order to solve some sort of a problem or be able to support something safely. But here in kinematics, we say that the kinematic analysis is really the first step in the design process, meaning it's really that layout work that we do. So we don't look at things in terms of necessarily even their actual size, but maybe fitting into some place or identifying a problem that we need to solve in terms of motion, okay? So in kinematics, things are going to be moving, but we're going to be concerned and focused on position, displacement. We're going to be calculating some velocities and accelerations later on of machine parts. And then additionally, we're going to be looking at, kind of standard machine parts that are used, gears and cams and belts and chains as well towards the end, okay? But really fundamentally, kinematics is that first step in our design process, okay? So we're going to keep things kind of at a fundamental level. So as we talk about machines are devices that are going to be used to alter, transmit, and direct forces to accomplish a specific object or objective. So like a chainsaw, for instance, is a machine that directs the forces to the chain so that cutting can occur, okay? And everything starts with the gasoline engine that is on there that's going to actually generate the power, the torque, the rotational speed, but then it's transmitted to the chain on that bar to actually do the cutting, okay? Now, a mechanism is the mechanical portion of the machine that has the function of transmitting that motion and the forces from that power source to wherever it's going to go to, okay? So the mechanism can be considered the rigid parts that are arranged and connected together that are going to go from that input to whatever the desired output is. Now, sometimes that motion can be rotational from the input source and then rotational on the output. Sometimes it's going to be rotational on the input, but then linear on the output. Okay, so we'll look at a lot of different looks at what mechanisms are and what they're comprised of. So in the case of a chainsaw, the mechanism takes that power from that small engine, and then it's going to deliver it to the cutting edge of the saw. Okay. Now, kinematic analysis is going to involve, as we said earlier, looking at position of things, how far they displace as we induce motion. what the rotation is going to be, whether it's how many degrees we move or how fast we might be moving in RPMs, for instance. Additionally, we're going to be looking at the speed of points or links themselves, as well as velocities and accelerations too. But notice that something's not on here. The amount of force is not on here. We're not worried about forces in kinematics, okay? Now in figure 1.2, and this is a similar illustration, but the figure 1.2 in your book, which is on page 2, at the top of page 2, if we were to just kind of look at the kinematic analysis of this item, kinematics is going to answer a couple of questions, okay? So we have this platform and it's going to go up and down vertically, right? And it's going to keep that platform at a horizontal, level. And so you'll notice here that we have a mechanism, a linkage that is going to allow this to move up and down relative to what we would call the frame down here, okay? And kinematics could kind of start that process and kind of identify, well, how high, what is the range of motion that we want this particular mechanism to go through, or where do we want that tabletop, that platform top, what's the lowest point, what's the highest point? That's a kinematics problem, okay? Not worried about how much we can put on there, not worried about, what the size of the steel rods on the side have to be, or the bars across, but we're worried about that spatial relationship, like what is the positioning? We also would be interested in, okay, depending on where we cross these two members, how is that going to affect the amount of travel that I get up and down? Or if we look, there's a cylinder here, okay? What does the travel of that cylinder have to be? What does the stroke of that cylinder have to be to obtain this up and down that I have? That's a kinematics problem. But notice we're not talking about what size is that cylinder, how much force does that cylinder have to have? No. It's just travel, displacement, position. We're starting there. First, it's like those first initial questions that we're asking about that final design, that final objective that we want to achieve, okay? All right, so if we go back to our PowerPoint, oops, sorry, wrong one. Did this before too. I'm gonna go here by my PDF. So what is the significance, it says here, of the length of the legs that support the platform? You don't have to answer these. This is like what kinematics would answer. Is it necessary for those support legs to cross and be connected at mid-span, or could you change where they actually connect? And how would that then alter the output of that displacement? How far must that cylinder extend to raise that platform? 8 inches, for instance, okay? So those are kinematic questions that would be answered through that process. Oops, check. Overall, do you want our calculations to be done in hand or on Excel? Most often it's going to be by hand, just so you know. We are, Excel is going to be used in this class, but we are not going to be Excel heavy. I don't know how you feel about that, but we are going to be on the side of generating our drawings using CAD, AutoCAD specifically, because we can use 2D here in these first steps of design. And then there are going to be some manual calculations. I am not opposed that if somebody is like a lover of Excel and wants to take the time to do that, it's okay. But I don't think we have a significant amount of problems that repeat, where it's going to create an efficiency for you. Does that make sense? So for the most part, it's going to be hand. Is that okay with you guys? I wonder how you feel about that. Is that okay? Okay. Like I said, we'll be using Excel on occasion and maybe even doing some because you guys had to have Excel before this already, right? That's like in our line of succession, right? Because you had statics already, which Excel is a prerequisite for, right? Just a really quick question. Did you use Excel a lot in statics? Really? Interesting.
Yeah.
What was that? Good. Good. Okay. All right. That's good to know. Thank you. Thank you. All right. Notice we're not dealing with the forces or the load carrying capabilities. We're only concerned with the required motion necessary to do the intended work. Okay. That's kinematics. All right. Now, let's talk about some mechanism terminology. So there's linkages, there's frames, there's links, there's joints. These are all things that we're going to be kind of talking about as we continue through the class, especially as we're creating our kinematic diagrams for these first chapters. So a linkage, first and foremost, is going to be a mechanism where all the parts are connected to form a closed chain. So the mechanisms that we're going to be looking at are all linkages. There aren't like open-endedness, if you would, to them. A frame is going to be one of the links in our mechanism, but it's not going to move. Okay, it's not going to move. So it's really our base. It's really going to be our foundation that we're going to be connecting to. The links themselves are going to be the individual parts that are probably going to move relative to each other in the mechanism. One of our links is always going to be the frame, which won't move, but then the rest of them, will have a place to move. And then a joint is going to be a movable connection between two links. Okay. And it's going to allow relative motion between those links. So you could have a pin joint where you have a pin going through and you have, two members that are going to rotate relative to each other. Or you could have a sliding joint where you would have, for instance, a linear bearing that is going to then, ride on that linear rail. And that's going to be a sliding joint then. Now, a simple link is going to be a rigid body that contains only two joints. So if we look at figure 1.5, I think I skipped one. Let me go back. We'll go underneath here. So on page 3, the top here, this is a pin joint. So we'll notice we have a pin going through here. We have two links, two members coming together, and they can rotate relative to each other. So that's an example of a pin joint. And then we have a sliding joint. So here we have a sliding block that is constrained for linear motion inside of kind of that rail that's there. Okay. And then as we go down to the bottom page here, or the bottom of the page, we have a simple link. A simple link is going to be a member that has two connections to joints. So this is a simple, so one on one end, one on the other. A complex link is going to be a link that has more than two connections to joints. So here we have 3 joints that it has on one member. Okay. And then additionally, back up here, these two are called higher order joints. This is a cam and a gear. Now, we specifically look at cams and gears towards the end of the class. So right now, during the kinematic analysis and the kinematic diagrams that we do here in chapter 1, and then it's going to be chapter 4 is going to be the second part of module 1. We are only going to be dealing with kind of those simple primary joints. Okay. Just because we dedicate time to these two subjects. Okay. But these are considered what we call higher order joints. So simple and complex links. Now, a point of interest on a diagram can be something that may not be like right in the mechanism of things, but we want to know something about it. So for instance, if we have a handle that extends out, we want to probably know if it's going to rotate about a center, like how far do we have to rotate it, or what's its travel going to be? If we have to move levers, how far do we have to move those levers that are going to be reasonable for an adult or whoever to do that? We don't want it to be too far apart that you have to extend too far. Okay, and so on. So points of interest are going to be identified on these diagrams as well. So let's look at kinematic diagrams specifically. So a kinematic diagram is going to be a stripped down version of a more complex machine or assembly. Okay, so if we look down at the bottom here, I've got a toggle clamp. Okay, and on the left hand side is what the toggle clamp looks like. So this handle goes up and down. Okay. And then it's going to take that clamp end and it's going to go up and down as well. All right. And the kinematic diagram for this would actually look like this. Doesn't look anything like it. It's a simplified version of. Okay. And we'll notice a couple things. First and foremost, as we look at this handle, notice how this extends out here and we have the letter Y. That's one of those special interest points where we would be interested in what is that handle doing? How far would I have to rotate that? What is the angle I have to go through, or what is the, the distance that I'm going to have to like push and pull that. Additionally, you're going to notice that down here is point X, and that is going to refer to the clamping edge in relationship to what we're going to call the frame, which is going to be the points that don't move. And notice here that X is out there. As the designer, you may even be concerned about another point of interest, which may be the top portion of this clamp part, okay? Whereas this rotates up, you don't want it to interfere with the handle side, okay? So that might be another point of interest. And as you get, you know, into these things and you're the designer for them, it'll become more apparent like what you're most interested in. Because a lot of times when we're in that kinematic analysis stage, again, the kind of that layout work, we're going to be interested in what is the travel of these things? Are they going to interfere with something? Is there going to be any collisions that are going to occur? And we may have to add a couple of, you know, additional special interest points to determine that. Okay. So kinematic diagram represents the variables that affect the primary function of a mechanism, but in a very simple form. A very simple form. So again, my toggle clamp put together looks very different than the kinematic diagram I would use, okay? Now let's look at example 1.1. And what we're gonna do is we're gonna go through the process of creating the kinematic diagram for this. And before we do so, we do wanna look at some of the standard symbols that we're gonna use for the different elements. So on page 5, there is table 1.1, and table 1.1 shows all the different variations of the standard ways that we're going to show elements on our diagrams. Okay, so first of all, a simple link. As we learned earlier, a simple link is going to be a member that just has 2 connection points to it. So many times a simple link is going to be just a straight member like we see here. Okay, and to represent that in a kinematic diagram, we are going to simply draw a straight line with 2 joints on either end. The joints, the primary joints, if it's a pin joint as we see here, it is going to just be a dot with a filled in circle. That's it, okay? A simple link that has a point of interest or a thickness here, notice that we have 2 places where we would have our primary joints, but then it's kind of got this, I guess what I call a dog leg. So you'll notice that we represent that with this kind of triangle looking. And then it also gives the idea that there is some thickness there without putting in the details of the thickness, okay? Because at this point, sometimes we don't know those details yet. Remember, we're in layout land, if you would, okay? Here we have a complex link. This complex link has 3 joints on it, okay? And it's going to be on each one of the corners here. Again, stripped down version of. And then we have a pin joint where we have 2 members coming together and they're joined by a pin. There's overlap here, but we're not concerned about that. Kinematic diagrams, we're keeping this simple. So we're focusing on the center of where that pin is, and we're just going to terminate that member right there. Okay, unless there's a reason to do it. If you have a special interest there that it could interfere with something or collide with something else that is, you know, in an assembly, then you may put that on there. Okay, or extend out beyond these, but most often we don't. Okay, simplified versions. Then as we turn the page, this is going to be a slider. Here we see a linear bearing. Now we're going to be representing these in CAD. So you'll notice that they have shading on things. So we're not going to be doing shading. Instead, at the bottom here, we're going to be adding hatch that is going to be at an angle with a distance apart. And I'll show you how to do that in AutoCAD. Okay. And then the last 2 here are our cam and our gear joints. And here as well, we won't really see these in these chapters immediately. We'll be looking at these a little bit later, but that's how we would represent those also in a simplified form. Okay. So this is going to be where you're going to want to probably look back to, you know, as you create some of these diagrams. So the example we're going to do is immediately below here. Okay. All right. And we're going to take this shear press right here, and we're going to draw a simplified version of, or a kinematic diagram of. So not sure if you guys have paper, but if you would like it, I encourage you to do this along with me, paper and pencil out. I know that the answer is in the book. If you look on the next page, there's a kinematic diagram over there of this, but I always think it's really nice to kind of go through the process so that you get this experience of kind of doing it. Does anybody need any paper at all? You do? Okay. I'll always have paper. There you go. Anybody need an extra pencil or anything like that? Good. Okay. All right. So first things first, we want to kind of go through and identify the different links that are here. And also, you know, what the frame member is and the types of links that we have. So, so where we start is exactly there. We want to know, where is our frame? Where is the part of this linkage or this mechanism that is going to remain stable? Okay. So looking at the operation of this, you're going to notice that this handle is going to go up and down, right? This is going to go up and down. And we can imagine that this blade then, this shear, is going to go up and down within the confines of these two vertical members, right? It's kind of trapped there. So this is going to have like rotational motion, and we would call that our input, because we have to actually actuate that handle in order to make this go up and down, right? That shear to go up and down. So that would be our input, and our shear would be the actual output. Okay. Now, as we look at that operation, there is a base here, and the base is right there and on this side, right? That's going to be what we call our frame. Okay. The frame doesn't move. Okay. Not all mechanisms are like that. If we look to our very next example, we're going to be looking at in a little bit. There's not an obvious frame on a vice grips, because it doesn't, like, you know, attach to something like to a table or to a base, but we'll talk about that in a little bit. But we are going to recognize that this member right here and this member right here, they don't move, and they have bolts on them. So it's kind of obvious, right? Now, in terms of what they look like, we have to kind of erase that from our mind. And the only thing we're concerned about is where any one of the other links connect to our frame. So the only place that we have a connection to the frame is actually right here at the end of that handle. Okay. So at that point, we are going to be representing that with a standard, if you would, a frame symbol. Okay. So we'll look at that. So this is our frame right here. Then we have our first link. Okay. Our first link is going to be attached to that frame member, and it's going to be this handle right here. Okay. This is a simple link because there are two joints connected to it. Okay. And then it's going to have this extension of that handle. So there'll probably be a special interest point there, because that's going to be like something we're going to be interested in its motion. Then you'll notice attached to that handle, we have, I'm going to call it a connecting rod. Okay. That connecting rod then is going to attach to this blade or this slider going up and down. Okay. So in this case, we've got a frame, we've got a handle, we've got a connecting rod, and we have a slider. We have 4 links in our mechanism. And even though the frame is not moving, it is considered a link. Okay. All right. So to create this kinematic diagram, so this is example 1.1. Okay. And we're going to start with our frame. So I'm going to put my frame like this. Now our frame is going to be something that has to look like it's anchored, like it's not going to move. And the standard frame symbol is going to look like this. Okay. So imagine when you draw it in CAD, and we'll be looking at AutoCAD in a little while after we get through some of this information and how this is going to look in AutoCAD. But we're going to draw basically a center point, a radius on the top, and then we're going to have it going down. And then we're going to have a horizontal, in this case, the way that it's sitting. And then underneath, we're going to put hatching. So it looks like it's like anchored. Okay. In the book, they're going to show shading all the time, but we're going to use hatching. So that's going to represent our frame. Okay. Then, and that's going to represent like this connection right here. Okay. That connection right there. Now we're going to draw our handle. Okay. And it has one of those, if you would, those dog legs in it, I call it. So we're going to show it's going straight up here. Okay. And then out like this. Okay. Out like that. This point right here is going to be one of the connections. So it's going to represent this right here. Okay. This next joint right there. And then this point out here is the end of our handle. And then we're just simply going to come back to that center point. So that's what our handle looks like. Okay. Now, You'll notice that if you peek over at their kinematic diagram, they do identify this point X right here. This is a special interest point. So special interest points are going to be like X, Y's, and Z's. Okay, the end of the alphabet. We're going to use the beginning of the alphabet to identify our joints in just a minute. Okay. Now we go back to our shear. And now we're going to represent this member right here, what I called the connecting rod earlier. And that's just going to be a straight line with the joints on either end, the pin joints on either end. So we're going to go like this. Okay, there it is. Okay, simplified. Now, in most cases, and really after chapter one, you're not going to have any dimensions for these diagrams. So you're just going to put them in and you're going to like kind of look proportional to what's there. Okay. But when we start and we look at our next, this part 2 of module 1 here in chapter 4, then you are going to have dimensions. Okay. Just so that you know. So for right now, we're just going to practice the diagrams as is. And then in chapter 4, we'll get more specific with sizing. Okay. And then the last member here that we have is this blade, and it's a slider. It's just going to go up and down. If we look up at the table, this sliding joint, we're going to represent that as a rectangle. Okay. Yes, there's a blade on it. And yes, the shape of it looks a little different, but we're just going to show it as a rectangle. And our rectangle instead is going to be going vertical instead of horizontal. Okay. So to draw that, we're going to put our pin at about the center, if you would. And again, I'm sketching here right now. And then we just have to show that it is vertically constrained, if you would, that it can only go in a vertical direction. So now this is what our slider would look like. Now, the only reason I put it on this left side was if I put it over here, there's other stuff going on. So you just kind of put it on the more convenient side that's open, where that frame is, that kind of that hatching is going to go. Okay, so now we have each one of our elements in place here. Okay, and as you can see, we rotate about this frame member. This is going to be always like our center of rotation. We're going to move this, and then through our connecting rod, that slider is going to go up and down. Now, a kinematic analysis of this and a question it would answer, and this is going to be chapter 4 type of work, is, okay, what's the highest point of this blade and what's the lowest point of this blade? Right? You'd want to know, as I rotate this around, when I go up with this, when I go down with this, what is the highest point of that blade? What's the lowest point of that blade? Okay, that's a kinematic question that you would answer, or layout, if you would, through that layout process. Now that we have all our elements in place, we need to label 2 things. We need to label all of our links, and we need to label all of our joints. Okay, so we're going to start with links. As I mentioned earlier, link number 1 is always going to be our frame. So our frame is right there. So we're going to put the number 1, sorry, I should do this neater, the number 1 with a circle around it. Okay, and that's how we're going to do it in CAD as well. And then after number 1, the frame is identified. The other members can be really in any order. Okay. The convention I like to stick with, and it doesn't mean that it's the only way to do it, but you're going to see the book isn't always consistent with this, but they start to get consistent after a while, is your input is usually going to be your next link, meaning the handle here connected to that frame would be link number 2. Okay. A number with a circle around it. Link number 3 then is going to go, and it's going to be that connecting rod. And then link number 4 is going to be our output, which is going to be that slider going up and down. Okay. So we have a 4-bar mechanism, this is called. And specifically, it's called a crank slider mechanism because the input is the crank and the output is going to be a slider, in this case, going up and down. And there, we'll see other classifications of 4-bar mechanisms a little bit later. What was that?
What's the reverse of that? What are you thinking of here?
It would be a slider crank. Yeah. Now we're going to be using and seeing a lot of 4-bar mechanisms because they're the most common and the most widely used. Okay, and you can come up with like an infinite number of different combinations and sizes and lengths and all that kind of stuff. So. Okay, then the next thing we need to do, we've got our links identified. We have 4 of them. The next thing we're going to do is we're going to identify our joints. Our joints are going to be identified with capital letters, starting with the letter A. Typically, you're going to start your first letter where you have your frame. And then again, from there, it becomes a little bit arbitrary, but then I kind of work from input to output. So my next link, or my next joint is going to be B. And then C is going to be the joint here at the slider, from that connecting rod to the slider. But there's one more joint. The last joint that we have, remember, there's a pin joint. That's what we just identified here, A, B, and C. And then there's also a sliding joint. Exactly. So this, I like to kind of point to it, and I'm going to call that D. Okay. Put a little arrow there. Or if you want to sneak it in right next to it, that's totally fine too. But don't forget about that fourth joint. Okay. All right. There it is. You did it. Okay. It's a kinematic diagram of your shear press. Now, if we look over here, this was the diagram that the book came up with, and ours is pretty close, right? Okay. A little bit later, after we kind of get through the chapter here, we'll look at AutoCAD, and we'll use that example to draw in AutoCAD to, see what that looks like. Okay. All right. This is fun. Aren't you excited? So good. So good. All right. Let's go back to our PowerPoint and see where we're at. All right, so we identified all these. We put our letters on, our numbers. Good, 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 good. Let's look at example 1.2. We're going to do that very same thing here, but this time we're going to be using a vice grips, okay? Vice grips. So as I mentioned earlier, when we look at that vice grips, there's not an obvious frame, okay? There's not an obvious frame. So when we have something like this, like a hand tool, what we're going to do is we're going to grab one of the pieces and we're going to say, this is the frame. And then the part that we're going to call the frame is going to be this top portion right here. Okay. The top portion right here. And if you would, you're going to hold it and you're going to let everything else kind of drag down below. Okay. You could do that with any other member truly, but it just kind of makes sense the way that it's sitting here, right here. That's the one that we're going to identify as our frame. Okay. All right. So by doing that, then I'm going to go underneath here. We're going to have to identify where those other links are connecting to the frame. Okay. So this is our frame right here. This is our frame member. There are two connections to the frame. There's this one and there's this one. Okay. And we're not going to connect the frame. We're just going to show two connections to the frames with that symbol that we learned just a little bit ago. Okay, so our next one here, this is going to be example 1.2. Okay, and just kind of by the nature of the way that it looks, I'm going to draw my frame symbol going up, and my my hatching is going to be on the top side for both of those, because everything else is kind of down below. It would get in the way. Otherwise, it wouldn't be wrong to do it like that, but just to kind of keep it a little bit cleaner and out of the way. So I'm going to draw my first frame member. It's going to be a horizontal line. And again, I'm sketching, so it doesn't have to be perfect. When you do it in AutoCAD, it will be perfect. Okay. So that's my frame member for that member on the left, or for that first connection on the left. And then we're just going to go at an angle here for the first connection. I'm going to draw this line right in between here down to where the handle is. Okay. And then it has a connection to the handle. All right. Now, as we look at the handle, it looks like these two joints are pretty close to each other. I know it might be kind of hard to see, but they're pretty like in line with each other. So I'm going to draw those two, but we have to get out here too what we would have as a special interest point, right? Because on this hand tool, what you want to do is you want to, look at the motion and make sure it's something that you can do with a single hand, right? Like if you would open your hand up and you would grip it, that you could, some adult hand could actually, actuate that. Okay. So we're going to make this kind of one of those extended triangles. So we're going to have the other connection point right here. We're going to connect those two, but then we're going to kind of draw a triangle out to here. What do I want to do? Yeah. And you might have to go something like this, so that we get a little bit of thickness, okay? Because we want to make sure that we get the impression that this is a single piece and not like two separate pieces that are, have a joint. If we wouldn't add kind of that thickness and you would just have it as a line, do you see how this looks like an individual member and then the other part would be an individual member? We want to give it this little bit of thickness so that we can see that it's all one piece. All right, so that's our handle. And then our handle is going to be connected to this bottom jaw part, okay? Now the bottom jaw part is going to be connected back to the frame, not to the same frame member. I mean, it's the same member, but it's a different part of the frame that we're connecting to. So we're going to draw another symbol for that joint right there. And then it is going to be connected to this point. And then we're going to have a special interest point out to the end of that bottom jaw. Okay. So we're going to draw another, let's see, this is going to go kind of straight up-ish. And it's pretty close to being in line as well. So we'll put this right about here. Draw our frame. Okay. Oops, down like that. And then we're going to draw triangle, and another special interest point will be down there. This will be the end of our jaw. Okay, yes.
The other end of it.
Yes, and we were just going to get there. You're so good. All right. So this would require you to take some measurements if we knew, exactly where it was, but you can draw this in, as kind of a reference. So if we go back over here, oopsie, wrong one. If we go back over here, you want to know, because you're going to want to find out like how far apart is this going to go, right? Like what the space is going to be in between there. So all you need to do is, because that's part of the frame, you would just show a frame member, something like that. And then you could add dimensions later on once we have some physical sizes to reference. And then like this distance would be, some sort of a reference. Yeah.
Could you do like where you draw that as like one of the squares, but have the hashing to show that it's a frame?
Yeah, you could. When you say squares,
Well, like,
kind of like the slider.
well, like,
Okay. All right.
like I kind of drew it like this, almost like where it was all one, or
Oh,
like even
oh.
if this had like depth. And
You
did
could,
that
yeah, okay,
here.
let me just put that underneath. So if you wanted to just extend this out, you could do that as well. Sure,
Okay.
sure, that would be fine. Now, typically the convention is you would not add that distance in between, but I know students like to do that. It's not really wrong to do that because yes, it's one continuous member, but you don't have to. We only have to do points back to the connections on the frame, just so you know. Okay. All right. So now we need to put our labels on. So special interest point, probably do an X and a Y, those 2 points. And then we want to add the numbers for each of our links. So number 1 is going to be our frame. Now, even though there's 2 connections to the frame, it's number 1 is the frame. That's it. Okay. Number 1 is the frame. We don't add another just because it's connected back to that same stationary link, if you would. Just by a frame member, because both of these signify frame. So you just want to put it by one of them. Number 2, now here's where it becomes arbitrary. But again, I kind of try to go to, okay, what's the first thing that's a part of the input that's connected to the frame? So number 2 would be here. Our input is technically the handle. The handle has that member in between it and the frame. So I'm calling that number 2. Number 3 would be our handle. And number 4 would be that bottom jaw. And then X and Y are those special interest points, as we said. Then we need to label our joints. Okay. What was that? Frame is always number 1. Like that's a non-negotiable. You can't call the frame number 2, 3, 4. It's always number 1. Yep.
So, but But you wouldn't label them each individually, you have 3.
Right. No. It's the frame is only once and you only put that on once. Kind of like you don't double dimension things, right? Even if we see them in more than one view. The frame, even though it's 2 separate connections to the frame, we only label it once. We only label it once. It's like if you would, the non-moving link in our linkage. Okay. Then we're going to put our letters, starting with, like I said, kind of that input side. I usually put by the frame, and then B, C, and then this one would be D. Okay. Let's take a peek. Let's see what theirs looks like. I don't think they put the top jaw in there, if I remember correctly. So yeah, they just did it very similar, right, to what we have here. So they've got 2 frames or connections back to the frame. They started on the other side. They called letter A on the other side. Again, those are kind of arbitrary, as long as later on we're going to also be doing calculations, especially when we're dealing with velocities and accelerations. We're going to be calculating those points. So as long as you have your A's, B's, and C's consistent with what you have in your diagram to what you're calculating, it's no problem. Okay. So here they called that joint A, then they went B, C, and D in this direction. And then they started with number 1 here. They called the handle number 2, the jaw number 3, and then that connecting point back number 4. Again, 2 through 4 are arbitrary. And then they have the 2 special interest points without really worrying about the top jaw. But I agree with you guys that top jaw is important, because usually want to know, like, how far is that going to open relative to how far I'm going to be moving that handle. Okay. Any questions? This is fun and good. All right. Let me go back over here. Logan, how are you doing online? Okay. Awesome. Okay. So now let's talk about mobility. Okay. Mobility is going to be identifying how many degrees of freedom are there left over after we have everything together. And it's going to be how many things do I have to do, if you would, in order to get this mechanism to properly function the way it needs to, or to do the job that it's intended to do. Okay. So degrees of freedom is the number of independent inputs required to precisely position all the links in that mechanism with respect to the frame or the ground. Okay. So when the configuration of a mechanism is completely defined, we position basically 1 link, and then we have 1 degree of freedom to do that entire thing. That is the best type of, if you would, configuration, meaning it's very user-friendly. I only have to move 1 thing. I only have to rotate 1 thing in order to get the rest of the mechanism to do what it's supposed to do. If I have to start doing 2, 3, and 4 things to get something in its final position, it's just more complex and harder to maneuver. Okay, so we try to make things as easy as possible whenever we're designing. Now, to determine what the mobility or the number of degrees of freedom that there are, we use an equation called Grubler's equation. Now, Grubler's equation, the variable for it is either F for degrees of freedom, or sometimes referred to as mobility, capital M. Our book uses mobility. I've always used F, but they're really the same thing. The rest of the equation, the equal to, is going to be 3 times n minus 1 minus 2 times jp minus jh. Okay, so what do those variables stand for? So degrees of freedom or mobility is F or M. N is going to be the number of links in your mechanism. So when we were just doing our kinematic diagrams, how many numbers did you put on there? Okay, all of them, the 2 that we've done so far, they've each had 4 links, right? 4 links. Number 1 is your frame. 2, 3, and 4 we had for each one. So that's the number of links in your mechanism. JP is going to be the number of primary joints. Primary joints are going to be those pin connections or the slider connections. So when we did that first one, we had an A, B, and C. Those were pins. And then we had a D, which was a sliding joint. Okay. And then JH, these are called higher order joints. These are when we have cams and gears. And as I said earlier, we're saving cams and gears for a little bit later in the class. So if we would have those, we would subtract those off as well. But for our purposes, that's going to be 0 for the work that we're going to be doing in these early chapters. Okay. Now, if our number for our degrees of freedom or our mobility is 1, that's called a constrained mechanism, okay? It's also considered like the best situation because again, we only have to do one thing. We maybe only have to attach a motor and we have to, you know, put this crank in a circle to make something go back and forth or rock or go in a circle as well. We do one thing to get that motion or that operation out of it. Constrained mechanism, 1 degree of freedom. A locked mechanism, if we end up with 0, that would be a frame, okay? That would be a frame member. It's not intended to move at all. And that's not a bad thing if it's doing exactly that. If it's something that's going to support something and we don't want it to move. And then we have unconstrained, and that's where it's going to be greater than 1. So if we get anything, a 2, a 3, a 4, that means I'm moving around a bunch of things in order to get it to do what it's supposed to do. Okay. All right. So let's look at calculating degrees of freedom. Before we go to example number 1.3, let's do the degrees of freedom on the 2 that we just did. Okay. So if we go back to example 1.1 underneath here. Okay. Here was that shear. Okay. That was this guy back here. We drew our kinematic diagram for it. And now we want to calculate the degrees of freedom or the mobility. So either F or M is equal to, and our equation is 3 times n minus 1 minus 2 times, I'm gonna move my D up here, 2 times JP minus JH, okay? Now, when you're doing this for me, because the assignment that you have, you're gonna draw the kinematic diagram and you're gonna calculate the mobility for each one of these problems, okay? At the end in assignment number 1. And when you calculate mobility for me or degrees of freedom, either an M or an F, I don't care which variable that you use. The book uses M, like I said, and I've always traditionally used F. But you need to write out your equation in variable form first. Okay, this is part of like showing your work for me. Now, when we do these kinematic diagrams, you're going to be creating these in AutoCAD. All right. If you wanted to add this calculation in AutoCAD as text, I don't care. That's totally fine. It's pretty simple algebra. Okay. But I want you to show me the work. So then the next line is going to be the numbers in place. So don't just start going F is equal to and just start putting numbers in for me. I want to know the equation you're starting with first and then put your numbers in. All right. So this is going to be 3 times N. This was the number of links. Okay, so I'm gonna just kind of put this here. This is my, oh my goodness, this is my links. Okay, this is my number of links. So N is the number of links. The links are the numbers with the circles around them. How many do I have in here? 4, right? I have 4 links. Number 1, remember the frame is always considered a link. It's a non-moving link, but it's part of the numbers that we put in here. So we're gonna have 4 minus 1 minus 2 times the primary joints. The primary joints are going to be pins and sliding joints. Sorry, pins and sliding joints. So in this case, we've got A as a pin, B as a pin, C as a pin, and D as a sliding joint. So we have 4 primary joints. And we do not have a cam or a gear, so you can just say that that goes to 0 or not included at all. I'm totally fine if you just stop this equation at 3 times n minus 1 minus 2 times JP and we're done, okay? Because there isn't any cams or gears in here, okay? All right, so now we're gonna do our math, okay? You guys have had calculus. Should be like piece of cake. So if we look here, we're gonna do what's in our parentheses first, right? Going left to right, order of operations, taking us back. So this is gonna be 3 times 3 is 9. 9 minus 2 times 4 is 8. So what's our number? 1, right? So what does this mean to us? If we go back to our PowerPoint, we go up here, it's a constraint. It has 1 degree of freedom. And if we look at this mechanism, the only thing we have to do to this is move that handle in order to get our up and down operation of that shear, right? And that makes sense to us. So 1 makes sense, okay? So that's a mobility equation. Let's do our next one here. Actually, I'm going to go back underneath here. Let's do the mobility equation for our vice grip. Okay. So we're gonna do F or M. Again, I don't care. I should just settle on one. All these years I've said this. I keep doing Fs, book does Ms. You wanna do F? I like F. Degrees of freedom. It sounds like more official than just mobility. Doesn't it? I don't know. I don't know. So our equation is going to be 3 times n minus 1 minus 2 times jp. And I'm going to leave off that end where we're not going to worry about that higher order joints. So here again, we're going to look, how many links do we have? So this is going to be 3 times 1, 2, 3, 4 minus 1 minus 2 times how many joints? How many letters do we have? 1, 2, 3, 4. So when we have a 4-bar mechanism, most often we're going to have a mobility or a degree of freedom of just 1. So we're going to have our F is equal to 1 again. Okay. Piece of cake, right? Remember when we looked at our assignment, I'm just gonna peek there right now because I know sometimes students look at the homework before they even worry about what we're going to learn, right? It's just natural. I do the same thing. If I go to assignment number 1, holy crap, that looks like a lot of work to do, right? It's not too bad. Notice that we have 1, 2, 3, 4, 5, 6 kinematic diagrams. Okay, that's what it says, they're kinematic diagrams. And then notice that we have 6 mobility equations. Guess what? It's the mobility equations for the diagrams up on top. So by doing the kinematic diagram and a mobility equation like we just did here, that's like 2 problems of that. Okay, just so you know. So the diagram is going to be worth 10 points, and then the corresponding mobility equation written out for me in the form that we have here is going to be 5 points. Okay, so in essence, I kind of look at it as really 6 problems as opposed to 12. Okay, it just looks like a lot. All right. So just so you know, as you're kind of thinking about that assignment. Okay. All right. So let's go back. Actually, I gotta go back over here. Go back to our module number 1, and I'll pull up our PowerPoint again. I really like Canvas, but I wish it would be, I don't know, a little bit easier to go back to where I was. So we did those 2 mobilities. We talked about that. So let's do this process for this toggle clamp. Okay. So if we look at our next example here, and this example is 1.3, it's on page 9. It's on page 9. If you want to peek ahead, if you have any questions, but I'm going to let you draw the kinematic diagram for this toggle clamp, what you think it is. If you want, put your hand over the bottom where the answer is, if you have the book, okay? And draw the kinematic diagram for what you believe this should look like, okay? And then we'll compare answers in just a little bit. And even if you peek and it doesn't look exactly like it, don't worry. There is more than one way of doing these things. So, so don't get too hung up on, oh my gosh, it's not the same as the book. Mine must be wrong. That's usually not the case. And then add your labels as you see they should be, whatever you feel. And then like, again, you can peek at the example in the book. Don't get too worried if yours isn't exactly the same. And then we'll compare. Make sure to add your labels for your joints as well. All right, let's, I'm gonna put mine on here. Mine looks a little different than the books. Mine looks like this. I did. So that clamping side over here, to me, as the designer, when I take that handle and I go up and down with it, I'm kind of concerned if these are gonna like hit when they come together potentially, right? So, so I included this part of the actual clamp portion, okay? And then came down to where the clamp would actually be and then came back. So it's not really they just were interested in where the clamping surface was. I was kind of concerned with the top of that clamp as well, because in operation, when this goes up, these are gonna kind of come together like this, right? And potentially they could hit each other, right? And I would kind of want to know if and when that happens. Okay, at least me as the designer. Again, this is layout work, and you might look at it differently. So this would still be an okay one, okay? And this would be okay, depending on what you're interested in. Everything else is the same. I don't know about the numbering and the lettering. They might have done it a little different. So they started, they have number 1 here, which is fine. Those are, notice that they didn't call out the frame twice, even though there's 2 connections to it. Neither did I, but I called my frame on this side, my connection over here, as number 1. Again, it doesn't matter, but number 1 is one of them. Then they started with number 2 as the clamp, number 3 as the handle, and then number 4 as that little like connector back to the frame. Okay. And I started in actually the very opposite way. I started with number 2 over here. 3 was my handle, and then 4 was my clamp. Again, I tend to look at it from input to output. All right. But it doesn't really matter. The only one that matters is which one. Which one is the only number that matters on this diagram? Number 1, always the frame, okay? And then our letters, they started A here, B, C, and D. I did exactly the opposite too. I started A here, B, C, and D, okay? So what you wanna do is you wanna look at your diagram and did you have the correct number of links? Yep, okay. Did you have the correct number of joints? As far as we know, right? Yep. And did we have number 1 called out as the frame? Yeah. Okay. All right. Now let's do our mobility equation. You probably know how to do that already too, right? So our mobility F is going to be equal to 3 times n minus 1 minus 2 times JP. Go ahead and fill in your numbers. And it's not a bad idea, even if you know it's going to come out to 1 and you look at it and you just kind of mindlessly put these on there, this will also check to see if you forgot anything. So if you don't have 4 links identified, then which one am I missing? Okay. If you don't have 4 joints identified, which one am I missing? Okay. So my F is equal to 1, as I would anticipate. And you should always kind of have an idea of how many degrees of freedom you should end up with. And you should end up with that number then. Okay, questions, comments, concerns, anything? I know you're so excited to get the homework started, aren't you?
Oh, are you gonna show us how you want it done?
Of course I am. Come on. This is like a full service operation. Okay, you're gonna get your money's worth, I promise. Okay. Let's go back to our PowerPoint and see where we're at. All right. Next problem, example 1.4. Example 1.4, if we turn the page. Okay. this is a can crusher. Okay, it's a can crusher. I'm gonna zoom in. All right. So, I mean, these come in a lot of different ways, but this is an example of a can crusher. And what we would do is, yes, it's got like a 3D element to it, but we would look straight on, if you would, for the view, like a front view of what that mechanism is look like. So my line of sight is going to be like right here. Okay, looking at it in that view. So you'll notice here that to operate this can crusher, we're going to take that lever and we're just going to pull it down, right? So how many degrees of freedom is that? 1, right? I do one thing. And so when I get to my mobility equation, after I draw my kinematic diagram, I better end up with 1, right? Okay. You'll also notice a couple of things here. We have what is this guy called? This is going to go up and down. We're going to have a slider, right? So we're going to have a crank, even though it's not going to go all the way around, it's going to oscillate, or it's going to rock, if you would. And then as we pull down on that crank, okay, or that handle, this slider is going to move, up and down. Or when I pull down on the handle, it's going to go down. When I release it and I put it back up, it's going to then go up, right? Okay. Where's my frame on here? There it is, right? It's actually the whole L here. This is one continuous piece, but we're not going to show it as one continuous piece. We're going to show a connection to the frame with our handle, and then we're just going to show a vertical line, random length, for our slider. Go ahead, draw the kinematic diagram for this. You're ready. Don't peek either. Don't cheat. Put your hand over the diagram down below. No. In this case, we're just going to show our standard rectangle for this slider. If there's an extension, we're going to have an example in our homework where we have a reciprocating saw, and the saw itself, which is an extension, is connected to the part that is like considered the slider, because the reciprocating saw, it's going to rotate, inside, but then it's going to go back and forth for the saw. And so in that case, on the end of our slider, we would extend out, and that would be a point of interest, because we would probably want to know how far out will that blade go and how far in would that blade go, right? But in this case, this is just kind of a standard block. This doesn't have like an extension on it. So yeah, not necessarily. And again, we don't have dimensions, so we're just going to draw this to just kind of represent it. There is a point of interest. You probably would be interested in the end of that handle though, right? Yeah. All right. I'm going to show mine over here. What do you guys think of mine? Now, I didn't put my labels on yet, but as I'm drawing this, do you notice anything about mine that you would improve? I heard it. Who said that?
Triangle.
Yes, the handle. Notice that if you don't put that triangle or kind of give it thickness to show that it's a single part, this kind of looks like two different members, right? Right? So by noticing that they add that little like triangle piece here, it makes it now a solid part, okay? Good. Then I'm going to add my labels. My frame is going to be number 1. I'm going to call the handle number 2, that connecting rod number 3, and my slider number 4. Okay. And then joints. A. I'm going to sneak B in here. C is here, and then we'll call that sliding joint D. Okay. And then the last part, well, and then we would have a special interest point X, right, up at the end of that handle. So how does this look to you guys? Any questions on the kinematic diagram? Okay. Mobility equation. Tell me what I'm going to write. I'm going to write 1 at the end, What's my equation? Variable form. 3 times n minus 1 minus 2 JP. Okay. So then I'm going to have 3 times number of links. There are 4 links, right? I wrote 4 numbers minus 1. So this is going to be 9 minus 2 times 1, 2, 3, 4 primary joints. Don't forget that sliding joint. Okay. And again, it's a nice check to be like, do I have 4 joints there? Right? I know it's going to be 1. There we go. Put a box around. Final answer. Okay. You guys cannot wait to do the homework. I can tell. You guys are like eager. I don't know. And you get to do 6 of them, 6 diagrams. It's going to be so good. All right, let's look back. Any questions on this example here? Kinematic diagrams, mobility. Fun, piece of cake. Good. All right. Let's go underneath here. All right, let's look a little bit at 4-bar mechanisms, kind of formalness of them. So the simplest and most common type of mechanism is called a 4-bar mechanism. Now, a 4-bar mechanism traditionally is going to have, and always have, the frame is going to be our number 1 link. And then this is where we start going from that input. The input crank is going to be number 2, or rocker, crank or rocker. Number 3 is going to be the coupler, or sometimes if we're looking at an arrangement where it's a piston, they call it a connecting rod. And then number 4 is going to be our output link, which could be a slider, or it could be a follower or rocker or a crank as well. Okay. So 4-bar mechanism always has 4 links to it. Now there's 4 types. Well, I'm sorry, there's 3 types. Wait, 3 types of 4-bar mechanisms. And if we look on, I don't have the page number identified. It's a little bit further. Now, this is where, as we look at our chapter, if we skip over sections, you're not responsible for them. If we skip over examples, don't worry about them. Just like go by. Okay. So, so you'll notice that this is at the top of page 20 is where illustrations of each one of these are. So there is double crank, there is crank rocker, and there is double rocker. So let's look at examples of each of these in our book. So at the top of page 20 is where we have some examples here. So we've got 2 double cranks identified here. These are these 2. The first one has our, what would be the smaller one is normally considered the crank or the input. So we have one smaller crank and then we have a larger input, but they both, when this mechanism is engaged, they're both going to create complete circles on the input and on the output. That's why it's called a double crank, because there's 2 cranks. They're both going around. A crank is when I'm going a full 360 degrees. Same thing over here. This is called a change point type of a mechanism, but the circles that they make are going to be equal in size. The next type that we have here is called a crank rocker. So on the input, this would be like maybe a motor going around. It's gonna be going in 360 degrees around all the time. But then the output is just going to oscillate or rock back and forth. Okay. It's not going to make a full circle. And then the next type is called a double rocker. Okay. A double rocker is where on our input, it's rocking or oscillating back and forth. And on our output, it's doing the very same thing. Okay. And then the triple rocker is when we are looking at, and we're seeing that connecting rod kind of fold over itself. And so it's also rocking as well. So each one of the movable links here is like rocking back and forth. Okay. So, so that's called a triple rocker. All right. So as we look at example 1.9, this is at the, it starts, the problem statement is at the bottom of page 20, but the illustration that we see here is at the top of page 21. And I think we've done a lot of drawing right now, so I'm going to skip this one on the drawing part. But what I want us to do is I want you to look at this mechanism and tell me which type of mechanism is this? How would you categorize it? Is it a crank rocker, a double crank, or a double rocker? What do you think? If you want to read the explanation at the bottom of the previous page, but this right here is a motor. Okay, this right here is a motor. I got crank rocker. Who thinks crank rocker? I got 2 people. Okay. All right. Any other possibilities? It's a crank something. It's a crank something. And sometimes it's not super obvious, right? And I say it's a crank something because we've got a motor right here, which means that what it's going to do is it's going to push this around in a complete circle, right? Okay. So we know that it's going to be a crank on this side, but it is a crank rocker because then this is going to oscillate back and forth, and it's going to either go up or it's going to go down. It's going to go up or it's going to go down. Okay. So a crank rocker in this case. Yeah. Okay. All right. The next type of popular 4-bar mechanism is called a crank rocker or a slider crank or a crank slider mechanism. And all that means is we have one of the elements is going to be going around in a circle for 360 degrees. And then the other side, the output most often is going to be a slider. So as we look at, I'm going to zoom out just a little bit right here. As we look at this mechanism, this is another type of a shear. Okay. But this is an offset slider crank mechanism where this is going to go around a full 360 degrees. And then this blade is going to go up and down within, you know, these rails linearly. Okay. So here it consists of a frame. Notice that our crank is connected to the frame. We have a crank. We have a connecting rod, and then we have a slider. Okay. And then additionally, we're going to have 1, 2, 3 pin joints, and then 1 slider joint. Okay. Now, since we have a 4-bar mechanism with 4 links and 4 primary joints, we still end up with just that 1 degree of freedom, meaning all we have to do is move that crank around and this thing is going to go up and down the way we want it to. Okay. All right. Now, techniques for mechanism analysis. So first and foremost, we're always going to, in this book, for the most part, when we get to velocities and accelerations, there's going to be some more calculations, but I've always taken the approach that as mechanical engineer, mechanical designers, you get a lot of calculations in statics, strength of materials, you know, those types of classes. So in kinematics, I tend to teach this more in a graphical sense. Okay. So we're going to be on the side of more drawing things as opposed to doing the analytic, calculating the math. So you'll notice that as you page through this chapter, they're going to have graphical solutions, but then they're going to have a section of analytical or math solutions. We're probably going to skip over most of the math because the drawings are there as well. Okay. And a lot of times when we're looking at engineering and we're looking at kinematic layouts, we are laying it out in CAD and our answers are there anyway. Okay. So unless you're looking for something super specific, and there will be opportunities, we'll get to do plenty of calculations. Don't worry. We are going to err on the side of graphical. Now, with that said, You can do manual solutions, okay, but you need a scale, a protractor, all that kind of stuff. And where you're at in the program, you all have had CAD, right? And so by using CAD, we're going to get more accurate results. So I am going to require you, when we do kinematic diagrams of any sort, which we're going to be using CAD probably almost in every one of these units here, we are going to be using, you know, the CAD, AutoCAD specifically, is because we only need 2D for this type of work, okay? So you will be required to use the CAD for your homework problems. If you're not given complete dimensions, as I had mentioned in this first chapter, the homework problems don't have dimensions on them. So you're just going to kind of put them in proportion, and you're going to draw them in those standard means that we had seen, you know, earlier as we were doing the sketches. Okay. So what I'm going to do is, we've really kind of gotten through the chapter stuff. The next video, the next section that we're going to talk about, and the video that I'm going to create, is going to be on, we're going to pull up AutoCAD, and we're going to start, you know, translating some of this stuff over there and showing what the diagrams are going to look like there. And then that'll give you a glimpse at how you're going to be handing in your homework. Okay. So I'm going to stop the camera or the recording right now, and we're going to take a break. Okay. Because we've been sitting for long enough, and we'll be back to do the other stuff. So I'm going to stop recording.